Hello everyone. In an earlier topic, we have studied the step-by-step process of instruction execution inside the CPU with the help of microprogramming technique. Today we are going to study how the control unit executes the micro instructions with the help of a microprogram, which is nothing but a sequence of micro instructions placed in the micro memory. Also, the various applications of microprogramming technique are explained. In the previous topic on microprogramming, we have studied the sequence of steps involved in fetch, execute, fetch operand and interrupt cycle from the instruction perspective. However, it is important to understand the role of control unit in each of these cycles. Let us consider the role of control unit in fetch cycle. The control unit does the following based on the input. First, the control signal opens the gate, allowing the contents of memory address register to be transferred to the address bus. Second, activate memory read control signal on the control bus. Third, the control signal to open the gate that allows the contents of the data bus to be stored in MBR. Fourth, control signal to the logic that increments the program counter by the instruction size and stores the result back to the program counter. The fetch operand cycle works similar. For the execute cycle, the control unit begins by examining code and on the basis of opcode decides which sequence of micro operations to perform the execute cycle. For the execution of an instruction during the execute cycle, the control unit receives input from the clock, the instruction register and the flex. With each cycle, the control unit reads all of its inputs and activates a set of control signals. The control unit controls the internal flow of data with the help of a switch or gate in every pair of registers. These paths are called internal data paths. Next, the control unit controls the operations of the ALU by a set of control unit signals. These signals activate various logical devices and gates within the ALU. Third, the control unit sends signal to the control bus for read and write operations. Thus, we have understood the control unit in terms of its input, output and the functions. Also, how its various functions coordinates and controls the execution of various instructions inside the CPU. Next, we learn how the functions of the control unit are implemented. Two of the most commonly used categories of implementing a control unit are hardwired implementation and second could be microprogrammed implementation. In a hardware implementation, the control unit is implemented with the help of combinational logic circuit. Its input logical symbols, which are the input to the control unit, are transferred into a set of output logical signal through the combinational circuit. Output logical signals are nothing but the control signal. As we have discussed earlier, the key inputs to the control unit are instruction register, the clock, the flags and the control bus signal. In case of flags and the control bus signal, each flag and its associated bit has some meaning. The instruction register contains opcode. Based on the opcode or the type of the instruction, the control unit decides the activation and the timing of various control signals. The control unit performs different actions for different types of opcodes. To simplify the control unit logic, there should be unique logical input for each opcode. The opcode with n bits will have 2 to the power n different unique instructions. The decoder hardware can take n bits of the instruction register as input and generate 2 to the power n unique outputs corresponding to every combination of opcode. Thus, to summarize, the control unit must control the state of the instruction cycle, which comprises of sub cycles like fetch, fetch operand, interrupt and the execute cycle. The control unit should also coordinate the timing of these sub cycles. The number of instructions in the CPU till 1970s and 80s increased manyfold. In a complex processor with large number of instructions, the number of Boolean equations needed to define the control unit was found to be very large. The task of implementing these Boolean equations using the combinational circuit was extremely difficult in those days, and therefore, in 70s and 80s, instead of implementing the control unit with a hardwired implementation, microprogramming was considered to be a cost effective alternative. The logic of the control unit and the sequencing is specified by a microprogram in the microprogramming technique. A microprogram consists of a sequence of instructions in a microprogramming language, and each such instruction is called micro instructions. These micro instructions are very simple instructions that specify micro operations. A microprogram instruction opcode bits are directly used to control signals required for instruction execution. These signals cause various register transfers and ALU operations. It was not only simple, but provided flexibility for the CPU designers to add new and complex instructions in the firmware. Changing the hardware implementation to add or remove instruction was very difficult, and therefore, during early 80s and late 70s, the microprogramming became quite popular after IBM announced the microprogrammed implementation in its IBM 370 model machines. Since then, the microprogramming has found applications in various segments. One of the important segment of where the microprogramming was extremely used is the use of microprogramming to implement the control unit of the processor. As we have seen earlier, it is very difficult, or in this during 70s and 80s, it was very difficult to implement the control unit using the hardwired implementation, and therefore, the microprogramming was considered a cost effective alternative. In order to understand a micro instruction, assume a simple instruction add B of 8085. The add B of 8085 implies that the contents of the accumulator must be added. Accumulator is register A, the register A must be added with register B, and the result should be produced through ALU, and it should be stored back in the accumulator register, which is A. In order to execute the instruction, if you carefully look at this instruction, the contents of the register A and B must first be copied to the inputs of the ALU. This is essential. The arithmetic and logical unit can only add two numbers if the two numbers are brought to the inputs of the ALU, and therefore, it is essential that the contents of register A and B must first be copied to the inputs of ALU. The ALU then must be instructed to perform the addition. Next, after the ALU has performed the addition, the result from ALU should be copied back to the register A. Imagine there are logical switches. Assume there are logical switches inside the CPU connecting register A and B with inputs of ALU. The contents of register A and B to be copied to the ALU requires these registers, which were earlier closed, must now be opened, so that the data transfer from register A and B to the input of ALU can take place. The ALU will then be instructed to perform the add operation again through some logical switch opened by the control unit. The output of ALU will then be transferred to the register A through a logical switch. Likewise, for all the instructions present inside a CPU, assume there are logical switches which must be closed to establish the data transfer, or if there are n such logical switches inside a CPU, the status of these switches can be represented by an n bit number, and if the control unit wants to on or off one of the register, then accordingly a n bit number can be generated from the control unit. Also, the opening and closing of these switches can be controlled by the n bit number. For example, in a particular micro operation, if out of 16 switches, we want the switch number 3, 5, 7 and 8 to be kept on and all other switches to be kept off, then the 16 bit number would look like as that it will only show out of 16 switches 3, 5 and 7 and 8 are on. That means, in a 16 bit number we can keep the bit number 3, 5, 7 and 8 as on and all other as 1 and all other bits can be kept as 0. This implies that if the control unit generates such a number where 3, 5, 7 and bits are kept 1 in a manner that control unit can make the switch number 3, 5, 7 and 8 as on and all other switches can be kept closed by the control unit. The execution of each instruction requires opening and closing of certain selective switches in a sequence. The n bit number represented as above can also be called a micro instruction to accomplish a particular micro operation. The instruction execution may require multiple micro operations. These micro operations are placed in the micro memory inside the CPU. Thus, for every instruction, the decoder logic should transfer the control signal to that portion of micro memory containing the sequence of micro instructions corresponding to that instruction. The sequence of these micro instructions is then executed one by one with the help of microprogram counter placed inside the CPU. Thus, to summarize, the architecture of a microprogram control unit can be explained as: first, to execute the instruction, the sequencing logic issues a read command to the control memory. The word whose address is specified in the control address register is read into the control buffer register. The contents of the control buffer register generates control signals and next address information for the sequential logical unit. The sequential logic unit loads a new address into the control register based on the next address information from the control buffer register and the ALU flags. All the steps are executed in one clock cycle. The last step either executes next micro instruction corresponding to this instruction. When the last micro instruction is executed, the control returns back to the macro instruction to be executed. The micro instruction, as explained earlier, comes under the category of horizontal micro instruction. In the horizontal microprogramming, each bit of the instruction drives a control signal and sets it on or off depending upon the status of the corresponding bit of the micro instruction. Sometimes the number of control signals are very high, leading to a larger micro instruction. In general, if there are n control signals, the size of the micro instruction will be n bits. However, there are not valid 2 to the power n combinations in the micro instruction set. The actual number of valid micro instructions may be x, and this x may be very small as compared to 2 to the power n. If x, which is the valid number of micro instruction, and it is very small, the valid combination of n bit micro instructions can be stored in the memory having x addresses. For addressing those x addresses, we can use log x to the base 2 bits to represent the address of every combination of the micro instruction. The size of the micro instruction may be reduced to log x bits only. However, the reference using log x bits must fetch the larger n bit micro instruction requiring a 2 level fetch hierarchy. The concept of making microprogram compact in size is called vertical microprogramming, as explained earlier. The vertical programming, though, can reduce the size of the program, but increases the complexity and time required to execute the micro instruction. Let us consider the example of a microprogram having p instructions of size n bits with only x number of valid n bit combinations. The horizontal microprogramming requires P into N into X bits of storage in micromemory, whereas the vertical microprogramming will require only P into X plus X into N, which is equal to X into P plus N, and it is very small as compared to the memory required for the horizontal programming. Next, we discuss the various applications of the microprogramming. Since the evolution of the microprogramming in late 60s, the concept of the microprogramming was first applied in the design of the control unit for the CPU. Later, the microprogramming concept has been applied in the variety of applications. The various applications of microprogramming include the realization of complex instructions, including complex instructions in the instruction set of the computer. Second is the emulation, emulating the hardware of some another machine on some hardware of a new machine is called emulation. The third is the operating system support. Fourth application of microprogramming was the realization of the special purpose devices. The fifth application of microprogramming was the high level language support. Sixth was the micro diagnostics, and seventh was user tailoring. As we have seen earlier, how a control unit can be designed with the help of microprogramming. The microprogramming provides the flexibility of adding and removing instructions by changing the contents of micro memory. Also, it allows us to add complex instructions in the instruction set of the CPU at ease, which otherwise may be very difficult to implement using hardwired implementation. Because of the cost effective alternative to the hardware implementation and the availability of the cheaper read only memory led to the popularity of the microprogramming in CISC processors in the 70s and 80s. The next application of microprogramming is emulation. The emulation refers to the use of microprogram on one machine to execute the program which was originally written for the another machine. The most common use of the emulator is to add users in migrating from one computer to another. Imagine, a user has invested millions of dollars in development of software in particular computer, and now another computer has come which is considered faster. Now, user finds it very difficult to migrate to the another computer, but through the concept of the microprogramming, emulators were developed to support the old machines. Users felt that okay, migration to the new computer will be very easy, and therefore, the emulation was one of the important application of microprogramming, and it commercially helped the users to migrate their software from the old machine to the new machine. Also, through emulation, we can help build a learning environment for another machine without the physical existence of that machine. When IBM announced 370 model, they provided an emulator for their old IBM 141041 on the new 370 model. This attracted the users to easily migrate their existing applications running on IBM 1401 to the new 370 model without any change in the software. The another area of microprogramming is developing frequently used and high performing primitive functions of the operating system directly as instructions using the microprogramming. That if it is there is an observation that out of 100 primitive functions of the operating system, if there are 10 functions which are heavily used throughout the day by large number of users, and if those important primitive functions are kept directly as microprograms inside the CPU, the overall performance of the operating system can improve, and therefore, this technique has potential to simplify the task of operating system and improve the performance. The microprogramming can also be used to implement special purpose devices. One such device could be a graphics workstation. The special purpose instructions for primitive graphics operations can be directly implemented in firmware using microprogramming concepts. Also, for scientific applications, floating point and complex functions can be directly implemented in firmware to improve the performance. The high level language support is another important application where microprogramming was found useful. The complex data types and the associated operations can be directly implemented as microprogram in the firmware. This firmware implementation can simplify the compiler's task of generating the machine level code. The compiler can produce time efficient as well as space efficient code with the help of these microprogramming concepts. Microprogramming can also be used or was used in the earlier microprocessor to support the monitoring, detection, isolation and repairing of system errors. These features are known as micro diagnostics, that during the execution of the CPU, if a fault occurs, then the fault detection logic, fault isolation logic and self repairing of faults can be directly implemented as firmware as a microprogram in the using the microprogramming techniques. These micro diagnostics help the hardware maintenance engineer to produce a variety of reports and help them troubleshoot and quickly fix the various issues arising because of the errors. Also, the approach permits to detect faults, repair them automatically and reconfigure to fix them on their own in many situations. Another application of microprogramming which was found useful in early 70s and 80s was user tailoring. To boost the performance of a scientific application, the frequently used and primitive complex functionality was directly fused in the firmware as microprogram. For an example, if a machine is purchased for weather forecasting purpose, the frequently used complex mathematical functions needed for weather forecasting software were fused in the firmware through the microprogram. So, to summarize, what we have learned today are the microprogramming concepts and its applications in various domains. One of the important component of any computing platform, whether it is laptop, palm top, tablet, desktop, mainframe or supercomputer, contains a central processing unit. The CPU is also called a single chip microprocessor. We have studied the various components of the CPU and how these components connected together execute an instruction. We have learned how an instruction is divided into micro operations and how these micro operations are implemented with the help of hardware or microprogram implementation. We learned the architecture of the control unit based on the microprogramming. The concepts related to micro instruction, micro memory and microprogram counter were introduced. Various applications of the microprogramming which have been used since last 30 years of the evolution of microprogramming were explained. Thank you.